Imagine the scene. It is March. You are sitting in the board exam hall. There is, pin drop silence everywhere.
Okay.
The invigilator is walking up and down the aisle, checking admit cards. You have the chemistry paper right in front of you. You are feeling good, maybe a little nervous, but mostly confident.
That is the best feeling. You have
Yeah.
done the revision. You are ready to write.
Exactly. You turn the page to section B, question number 5, and you see a formula printed there, Cohen 33 plus full.
Okay.
The question is very simple, just one remark. What is the coordination number of cobalt in this compound?
Okay. A standard classic question.
So you look at the bracket, you see N is the ligand, you see the subscript 3 written next to it.
Right.
That means there are 3 molecules of N. So logically, using your common sense, you pick up your pen and write 3. You come out of the hall thinking, marks secured, and guess what happens when the results come?
You get a big round 0 on that question.
0. And the worst part is, when you check the answer key or ask your topper friend later, they say the answer is 6. And you were standing there thinking, how is that even possible? I can see the number 3 with my own eyes. Is this some kind of a trick question?
It is not a trick, and it is certainly not a printing mistake.
Yeah.
But it is definitely a trap.
A trap.
It's a concept mistake that catches almost every student off guard.
A trap.
Yes.
Mm-hmm.
Because, my friend, you counted the guests at the party, but you forgot to count the handshakes.
Guests versus handshakes. Okay. That sounds like a riddle we need to solve.
We do. Welcome to the deep dive. Today, we are cracking open Unit 5, coordination compounds. But we are not trying to, memorize the entire NSERD textbook in one go.
No.
That is a recipe for disaster.
Absolutely. You cannot digest this whole chapter in one sitting.
Today, our mission is very specific. We are focusing strictly on the definitions of important terms.
Okay.
Because if you don't know the vocabulary, this chapter is basically an alien language.
It is like trying to learn coding without knowing what a variable or a function is. You will just be staring on the screen.
Precisely. If you don't know these specific definitions, you cannot calculate the coordination number, you can't do the IUPAC naming, and you definitely cannot predict the shape or the hybridization.
You're completely lost.
Completely lost in the exam.
So think of this episode as building your parts list. Before we build the engine, or even understand how it runs, we need to know the difference between a nut, a bolt, and a washer.
Correct. So let's look at the parts list for a coordination compound.
Let's start from absolute 0. When we see those score brackets in a formula, what are we actually looking at structurally? What is the picture in our head?
Imagine a solar system. Or, to make it more relatable to our daily life, imagine a very strict corporate office.
Okay.
At the very center, sitting in the big chair, you have the boss.
The boss, okay.
That is your central metal, atom, or ion. Usually this is a transition metal from the D block like iron, copper, cobalt, nickel. They are the center of attention. Everything revolves around them.
Okay, so the metal is the boss. Who are the employees then?
Surrounding the boss are the ligands. These are the molecules or ions that are attached to the metal.
The assistants.
They're the assistants. They gather around the central metal to support it.
Okay. Ligands are the assistants. Now, this brings us to the definition that causes the exam trap we talked about earlier.
The coordination number.
The coordination number, yes.
The one most students get wrong.
So why isn't it just the number of ligands? If I have 3 assistants standing around me, surely my number is 3.
In a normal room, yes. But in chemistry, the coordination number is not the count of molecules. It is the count of donor atoms directly bonded to the metal.
Wait, let's distinguish that clearly. Donor atoms versus molecules.
See, think about the bond itself.
Yeah.
In this relationship, the central metal is basically an electron pair acceptor.
Okay.
It has empty orbitals. It's like the boss has empty hands, waiting to receive files.
Okay, empty hands waiting for something.
And the ligand is the electron pair donor. It brings a gift, a lone pair of electrons, and shares it with the metal. That sharing creates the bond.
The coordinate covalent bond?
That's it. So the metal says, I have space, and the ligand says, I have electrons to give.
Right.
Exactly. Now, here is the anchor definition you need to write in the exam if they ask, what is a ligand? A ligand is a molecule or ion capable of donating a lone pair of electrons to the central metal.
And the coordination number.
It is the total number of ligand donor atoms to which the metal is directly bonded.
Okay, I think I am starting to see where the confusion happens. In that cobalt question, I was counting the on molecules.
Yes.
I was counting the people in the room.
Right. You're counting the bodies.
Yeah.
But you need to count the hands that are shaking the boss's hand.
The handshakes.
The handshakes. Let's look at N closely. Do you know what N actually stands for?
Ethylenidamine.
Right. Ethylenidamine. It is 1 molecule.
Yeah.
But if you look at its chemical structure, picture a chain. You have a carbon chain in the middle.
Okay.
But on the left side, there is an agamine group, NH2. And on the right side, there's another anomine group, NH2.
And nitrogen has a lone pair.
Exactly. Both nitrogen atoms have lone pairs. So this one molecule has two separate hands capable of grabbing the metal at the same time.
Oh, so it is like one person walking up to the boss and shaking the boss's hand with both of their hands simultaneously.
Perfect analogy. One guest, two handshakes.
So if I have 3 of these on molecules,
3 guests.
each shaking with 2 hands,
So 3 into 2 is?
6. The coordination number is 6.
There you go. You counted the handshakes, not just the guests. That is how you get full marks.
Man, that is actually quite sneaky if you aren't paying attention to the structure.
It is.
But it makes total sense now. You have to look at the denticity of the lichen, not just the formula.
100%. You cannot just count the subscripts.
So we need a way to keep this hierarchy clear in our heads. Because in the exam pressure, when the clock is ticking, it is easy to mix things up.
I always tell my students to visualize a busy restaurant kitchen.
A kitchen.
It helps you see the difference between the people and the jobs they do.
Okay, I like food analogies. Set the scene for us.
Okay. In the center of the kitchen, you have the head chef. That is your central metal atom. They are standing in the middle shouting orders.
In charge.
They are in charge.
Head chef is the metal.
Got it. Then, swarming around the head chef, you have the sous chefs. These are your leggings.
The helper.
They are there to help, to contribute their skills.
Right. Sous chefs are the leggings.
Now, the coordination number is the immediate staff count. But think of it as the number of stations being managed directly under the head chef's supervision.
Okay, so if the head chef has 6 stations running, chopping, frying, plating, and so on, the coordination number is 6.
Correct. Now, here is where the vocabulary gets technical. Not all sous chefs are the same, right?
Oh, so?
Some sous chefs are just beginners. They can only handle one station at a time.
Okay.
Maybe just chopping onions. We call these monodentate ligands.
Mono means one.
And dentate comes from the Latin word dens, meaning tooth.
Tooth. Like biting.
Exactly. It refers to how many teeth the ligand uses to bite onto the metal. A monodentate ligand bites with one tooth.
It occupies one station in our kitchen.
One person, one station, like
Like-
ammonia or water. Standard sous chefs.
Okay.
But then you have the bidentate ligands. These are the specialist chefs. This is one person, one physical human being, but they are so talented they handle 2 stations at once.
Like a multitasking pro.
Yes. Maybe they're chopping with the left hand and stirring the sauce with the right hand.
So they are taking up TWO spots on the counter.
Correct. So even though it is just one chef, they are filling 2 slots in the coordination number.
Ah! And ethylenediamine, our friend, is that specialist chef.
It is bead and take. 1 molecule, 2 bites. So if the head chef has room for 6 stations, you only need 3 of these specialist chefs to fill the kitchen completely.
That is a brilliant way to think about it. So we
Yeah.
need these words, monodentate, bidentate, polydentate, because otherwise we can't describe how full the metal actually is.
Exactly. Without denticity, chemists couldn't describe the geometry or the structure. We wouldn't know if the parking lot is full or if we can squeeze another car in.
Precision is everything in chemistry.
It is.
Let's try to visualize this at the particle level. Can we do a mental movie? I want the listeners to really see this happening in 3D.
Let's do it. Close your eyes for a second, listener. Imagine you are microscopic. You are floating inside a beaker of water.
Okay, I am diving in. What do I see?
In the center of your view, you see a glowing, pale green sphere. That is an iron ion, Fe2+.
Here.
It is floating there and has these empty magnetic zones around it, docking points.
The empty orbitals. The head chef waiting for staff.
Right. Now look around. Floating past you, you see ammonia molecules. Visualize them as small spheres with a single bright blue dot on their face. That blue dot is the lone pair.
Single blue dot. Monodentate. 1 grabber.
Correct. Now look over to the left. You see molecules ethylenediamine. They look different. They are shaped like tweezers or a flexible U shape. And they have a blue dot at each end of the tweezer.
Bidentate. 2 grabbers on the same tool.
And then, floating in the distance,
Mm.
a giant monster molecule, EDTA.
Whoa.
This thing is huge. It has 6 blue dots all over it, hexadentate.
6. That is a beast.
Now watch the action. They swarm the metal. An ammonia molecule comes in. Look at its single blue dot, locks into a docking point. But watch the N molecule. It comes in and click, click. Both ends snap onto the metal at the same time.
Like a clamp.
Exactly like a clamp. And that clamping action is actually called chelation. It comes from the Greek word chele, meaning claw.
The ligand literally claws onto the metal.
Yes. And that visual really helps. The end isn't just touching the metal, it is wrapping around it.
Right.
And when 6 docking points are filled, whether by 6 ammonias or 3 M molecules or just one giant EDTA, the metal is full. The complex is locked.
So do we actually see this happening, or is this just theory for the textbook?
You see the results of it all the time.
Yeah.
Have you done the copper sulfate experiment in the lab?
Oh, the blue crystals. Definitely. Every Class 12 student has done that practical.
Let's break down the magic there. You start with white anhydrous copper sulfate.
Right.
You add water, and it turns a nice light blue. That is coordination chemistry.
Right.
The copper ion is the metal. The water molecules are acting as ligands.
So the water is the first crew of sous chefs.
Exactly.
Right.
But then, in the practical, you add ammonia to that solution.
Yeah.
And suddenly, what happens?
It turns that deep, deep blue, almost violet. It's a huge change.
Why? Because the chefs changed. Ammonia is a stronger ligand than water. Comes in, kicks the water out, and takes the spots around the copper.
So the color changes because the parts list change.
That's it. Ammonia instead of water. You're literally seeing the ligands swapping places with your own eyes.
That is so cool when you think about it. It is like a substitution on a cricket field, and the team jersey changes color instantly.
That is a great comparison. But there is an even more powerful example, a life-saving one.
Oh.
We talked about EDTA, the giant hexadentate ligand with 6 teeth.
The beast with 6 blue dots.
That beast saves lives in cases of lead poisoning.
Really?
Well, imagine a child accidentally swallows lead paint chips. The lead ions enter the bloodstream. Lead is toxic. It damages the brain.
Right.
We need to grab those lead ions and get them out of the body fast. So doctors inject EDTA.
Okay.
Because EDTA has 6 teeth, it wraps around the lead ion like a cage. It uses all 6 connections at once. Click, 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 click.
So the lead is trapped inside this molecule cage.
Completely trapped. This is the power of chelation. Because it is so tightly held, the lead cannot react with the body tissues anymore. It just floats through the blood, harmlessly, and is excreted by the kidneys.
Wow. So if EDTA was just monodentate, if it only had one tooth, the lead might slip away.
Exactly. A monodentate ligand might hold the lead for a second, but the lead could let go and grab onto a protein in the brain instead. But the high denticity of EDTA, the claw effect, locks it down permanently.
That stability is what saves the patient.
Yes.
That is incredible. It is not just for marks, it is actual medical technology.
Yeah, precisely. Chemistry's everywhere.
Yeah. Okay, I want to circle back to our trap question one more time, just to be absolutely sure we've got it locked for the board exam. Cohen 33 plus sneaker.
Yeah. Yes.
In the exam heat, you see 3 N's. Your brain screams, answer is 3.
And you have to stop your brain. You have to say, hey, check the denticity.
Right. I checked the parts list. N is badentate. It has 2 nitrogen donors, so 3 molecules times 2 donors each equals 6.
Total donors equals 6. Coordination number equals 6. Full marks.
Awesome. Okay, let's do a quick clarity check session. Rapid fire. These are the golden rules you need to memorize for the definition section.
I am ready.
Clarity check 1. What exactly is the coordination number?
Coordination number is the number of donor atoms directly bonded to the metal. Do not count the number of ligand molecules. Count the atoms touching the metal.
Clarity check 2. How do I classify the types of ligands?
Remember denticity. Monodentate equals 1 donor atom, like water. Bidentate equals 2 donor atoms, like N. Polydentate equals many donor atoms, like EDTA.
Clarity check 3. This one confuses people. Does a ligand have to be negative, like an anion?
No. This is a very common misconception. Neutral molecules like ammonia and water are excellent ligands. A ligand just needs a lone pair of electrons to donate. It does not necessarily need a negative charge.
Right. So don't ignore the neutral ones. And finally, clarity check 4. What is the complex ion?
The complex ion is the whole package inside the square brackets. It is the metal plus the ligands. It usually carries an overall charge.
Okay.
Don't confuse the complex ion with the counter ions that might be floating outside the bracket.
So if it is NH3 6Cl3.
The thing in the bracket is the complex ion. The Cl3 outside is just the counter ion, the ionization sphere. They're separate things.
Okay, that clarifies a lot. I feel much more confident about tackling these definition questions now.
Good. See, the vocabulary is the foundation. Once you have these terms locked in, the rest of the unit, isomerism, crystal field theory, it all becomes much easier because you speak the language.
Let's recap quickly before we sign off.
Sure.
Today we looked at Unit 5 definitions. We learned that a coordination compound is like a hierarchy. The central metal, is the boss or head chef.
And the ligands are the staff or sous chefs.
We learn that the coordination number is the number of handshakes, not the number of people.
Right. And we met the bidentate specialist chefs like N and the hexadentate beast EDTA, which uses its claw-like chelation to trap lead and save lives.
And the golden rule for the exam: always count the teeth, the donor atoms, never just the heads, the molecules, to find the coordination number.
That is the takeaway.
So next time you drink a glass of water or you see a color change in the chemistry lab, remember, there's a whole swarm of ligands biting onto metal ions right in front of you.
And remember, in chemistry, as in life, it is not about how many friends you have. Those are just the molecules. It is about how many strong connections you make. Those are the donor atoms.
Ooh, deep thought to end on. I love it. We will be back with more deep dives into the rest of this chapter soon.
Goodbye. Keep
But-
learning.